Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. In this video, I am going to show you how the backpropagation algorithm works internally. We'll look at backpropagation classic, also atom, Nesterov momentum, and other techniques that are commonly used to train deep neural networks.
For the latest on my AI course and projects, click subscribe and the bell next to it to be notified of every new video.
So classic backpropagation. Backpropagation has been around for a while. It is, Jeffrey Heaton contributed quite a bit to it, and Werbos as well. So a variety of people introduced aspects of backpropagation, and it has been continued to be built upon over many years. This equation that you see here is sort of your very general training equation. This just says that t, now t is the current epoch or time. This is saying that the weights, which are the weights of theta, the weights for the current time are equal to the weights from the previous time minus v, the current time. V from the current time is just a vector. All of these are vectors that holds the amounts that we're going to change each of the weights by. So this doesn't tell us a whole lot by itself. It just says that we are going to change the weights at each time by this vector of change amounts. Now the vector of change amounts, v sub t, we'll see a variety of functions that show us how to calculate v sub t. The first is classic backpropagation. So if we look at this, this is gradient descent. So you have eta multiplied by, now eta is multiplied by the rest of this. This is essentially one unit. This is not this thing multiplied by the j function. This is the nabla, or the upside down delta, or the harp-shaped operator. This says take the gradients of the loss function with respect to the weights from the previous time step or the previous epoch. So this is essentially giving you all of the gradients multiplied by the learning rate, eta. Common values for the learning rate are these, 0.1, 0.01. Rarely would you ever want to make that 1 so that you're fully adding the gradients to the weights. That would simply be too chaotic. Now let's see really what the gradient is and how it's actually used. This is a derivative. It's a partial derivative. So you always take the partial derivative of one multivariate calculus. You take the derivative of one single variable in a multivariable expression, so one single weight with all other weights held constant. So this shows you essentially the error function for a particular weight. So the error for this weight, as you adjust the weight, so if you make the weight 0, the error is going to be here, then it goes up, and then it swings way down. This is potentially true. As you vary just one weight in the neural network, the error function will go up, down, and change its value. Typically, we're doing gradient descent, so we want to get the weight all the way to the lowest point here. Now, we don't want to generate this entire graph and sample the neural network at each of these points. That would be computationally expensive because there is a different chart of this for every single weight in the entire neural network. And as you change one weight, all the others potentially change too. This is where you have to do the partial derivative. We're doing the partial derivative for just one weight. Say the weight was currently at 1.5. So all we would know is that the error was here. We don't have the rest of the lead up or continuation of the chart. We just have this one point. That point doesn't tell us too much until we take the derivative of the loss function. Then that tells us the instantaneous rate of change. So you've got the slope of this point right here on the error function curve. Notice this line has a negative slope. But if we just added that gradient to it, the negative value, whatever that negative slope is, that would decrease the weight. It would go in the wrong direction. So if you truly want to go this direction, because we're past just a little bit of the crest of that hill, if you want to go in this direction, you need to take the opposite of the slope. That is why up here we're subtracting v sub t. Because if this, say we're right here, then the line would be very much this direction, and that would be a very negatively sloped line. You would want a positive number, so you continued on your way down. If we were right here, then the slope would be positive. but we would want to subtract 1 from the weight to continue along this direction. So that is classic backpropagation. It's governed by the learning rate. If you made your learning rate too big, instead of gradient descending down here, you'd probably jump completely to the other side of it, and you would never find your way down to this lower value. So learning rate just describes how quickly we're going to attempt to push the weights to optimal values. And this link is pretty handy. It shows a JavaScript application that I wrote that takes you through all the steps of classic backpropagation, so you can see literally how an entire neural network is calculated for XOR. Next is momentum propagation, backpropagation. So momentum is something that was added to backpropagation to prevent from being settling into a local minima. So local minima could be right here. It might be that further over here there'd be an even more optimal value, but once the weight gets settled into here, it's really hard for it to push its way completely out of that valley and continue on training. We have the case here. The weight, which is where that ball currently is at, is essentially stuck in a local minimum. There might be a global minimum here. It's really hard to know where the global minimum is. It's usually almost impossible. So this weight would have been continuing down, 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 but it would potentially get stuck here if not for the momentum that pushes it over the hump and allows it to continue. Momentum, just as its name implies, you can think of these weights as moving through high dimension space. Momentum just gives the weight push and continues that push as it maintains its momentum. This is the formula for momentum. Now we have 2 hyperparameters. We have eta, which is the learning rate, but we also have lambda, which is the momentum rate. The first part of this is completely the same as classic backpropagation. You are simply taking the gradient multiplied by the learning rate. But you have this additional term here, and this is the momentum term. This is lambda times vt minus 1. So whatever our previous delta, our previous update was, we're scaling it by lambda and adding it. You're just adding the last update scaled right onto the equation with everything else. That's really all that momentum is. So as you were moving down this, you would have built up a lot of momentum because you would potentially be moving down fairly fast. Then that change is very much a positive weight that would keep getting added onto the weight and hopefully push it over the hump and onto possibly out of the local minima and onto a better situation, hopefully. By the way, very common value for momentum is 0.9. They usually favor a fair amount of momentum, whereas learning rate is often much smaller. It's usually 0.1, 0.01, or some other negative power of 10. Next, we're going to look at batch and online backpropagation. So this is an important concept for propagation training. We'll see later that we can configure these values in TensorFlow and determine what the batch sizes will be. Batch is simply how many training set elements do you need to go through. So each of these gradients that we're calculating is for a single training set element. So you might have 1,000 elements in your training set. How many of those, you don't have to literally update the weights every single time you calculate a training row and get the deltas to the weight. You can batch those up, and you batch them up simply by summing up the gradients. So you process the first row of training data, and you get a vector of gradients equal to, or changes, the v, equal to the size of the weights. And you can calculate the next training row, and you add those gradients onto whatever you had before. You keep vector adding the gradients until you've made it to the batch size. So a batch size, if you had a batch size of 10, that means as it's going through the training set, it'll make it through 10 elements. And then at the end of the 10 elements, it has the gradients that are basically the sum of that whole run. And then it will apply the changes to the weights. Online training simply applies the change to the weight as soon as you calculate the gradient. Just one at a time. Calculate a gradient for one training row, apply it to the weights, move on to the next training row, calculate its gradients, add it to the weights, and continue. Having the batch sizes, this can provide considerable efficiency to the training of the neural network. This is also very big data compliant, because if you've got a very, very large data set. You just need to randomly sample many batches from it. So many batch training, that's another very common technique for training neural networks. Many batches are typically between 32 and 64 in size, so they're relatively small. Step and iteration, that is just how many training cycles has the neural network gone through. Step, iteration, or even, and then. All right, now we'll look at stochastic gradient descent, which is often used in conjunction with many batch training. Stochastic gradient descent is used it provides a very stochastic or random descent. What's happening is rather than calculating the gradients with the entire data set, you just pick small groups and you keep going through these random samples with replacement of the neural network training data. And as you go through each of these one by one, the error will decrease. It'll go up sometimes. Sometimes you'll pick particularly bad sets of training data. Sometimes you'll pick particularly good sets. It just all pretty much depends. So stochastic gradient descent is often used alone or as part of another training. It's computationally efficient and it decreases overfitting by focusing only on a small number of relatively good weights. And also there's a variety of other techniques. Like I said, backpropagation and gradient descent, that's just the main backbone. Some of these other techniques, what they attempt to solve is the learning rate and momentum. These are both hyperparameters. These are numbers that you need to tune along with everything else. You thought it was bad enough that you had to pick how many hidden layers and how many neurons you want on each hidden layer. Now you've got a learning rate and momentum, and you need to figure out what the best learning rate is, what the best momentum is, so that you will be able to effectively train this neural network. The problem is the learning rate, if you adjust it too small, it's never going to accurately train your neural network. It's just not taking enough risk. If you make it too large, your neural network will be very, very erratic. And momentum, same thing. If you make it too large, things become erratic. If you make it too small, it's not really having an effect. Also, if you think about it, this learning rate is being applied to every weight in the entire neural network. Maybe a single learning rate is not enough. Maybe some neurons are learning faster than others. So they like a concept of putting in multiple learning rates. Or you can also, sometimes you'll see that they will just automatically decrease the learning rate as training progresses. So we're trying to move away from having every weight having a global learning rate and momentum, and then also move to making those values very sensitive, very non-sensitive, or very accommodating to values that weren't chosen so well. These are some other training techniques that I've worked with in the past. There's resilient propagation. It works pretty well. It basically recognizes that the sign of the gradient is probably the most important thing. It tells you which direction the weight should move to better optimize. It also does not need a learning rate and momentum. So it was popular back in the day. It's not seen as much use with deep learning. Nesterov accelerated gradient, what that does is with stochastic gradient descent, it helps to mitigate the risk of just picking a really bad mini batch that then damages the rest of the training that you've done. There's AdaGrad and AdaDelta. These are both AdaGrad basically it keeps a per weight decaying learning rate, but it's monotonically decreasing. It never increases again. So that's why AdaDelta was created, to address AdaGrad's issues where that learning rate could just go in a direction and decrease to pretty much zero. There's also non-gradient methods. If you can't take a derivative of your loss function, these might be useful. This includes simulated annealing, genetic algorithms, particle swarm, Neldermead, and many more. So the atom update rule, talked about before, classic backpropagation. It's just another way of calculating V to put into this weight update algorithm that we had before. Now the atom update rule, what is very nice about it is you don't really have to focus too much on a learning rate. There is a learning rate present, but of the values that you have, the authors of the original paper, Kingma and Ba, they give some good recommendations for the hyperparameters, and I rarely, even that learning rate at the end, 10 to the -8, you often do not have to change those. This is a relatively new training algorithm. It was introduced in 2014. It's a popular one. It deals with training for sparse data where lots of missing values, and then also stochastic. error function. The error function is stochastic because we're doing stochastic gradient descent. So we're constantly randomly subsampling a batch size, a mini batch, and updating the neural network based on that. So the changes that you make from one iteration to the other might not help because you're grabbing a different set of training data on each one. The paper for this is given here at Cornell University, the archive. If you haven't dealt with archive before, that's the Greek letter chi, so archive. And moment estimation, method of moments that you see here, it's a way of estimating each of the moments of a distribution of values. So that's the mean, the variance, and so on. So let's look at the actual paper for this. This is very similar to the code that we've seen for the other ones. So this is just t equals t plus 1. That's indicating that we're moving through the time. We're initializing the first and second moments. The first moment is the mean, so the mean of the gradients that you're trying to estimate. And v is the variance, so the second moment. There is a third and additional moments, but all we're dealing with are these two, the first two moments. By the way, that's where the name ADAM comes from, adaptive moment estimation. And then we initialize the time set to 0. So these two initial estimates are 0. We are going to calculate the g, the gradient. So this is the gradient, just like we're doing before. Very similar to classic backpropagation, a little bit different terminology. Instead of the j that I use, they use f. So this is the loss function with the weights. That's exactly the notation from the module for the previous one. And we are going to get that gradient. These two values deal with a bias that occurs early on. Since these are initialized to 0, that creates a tremendous bias towards 0. So these are just two I'm sorry, the hats down here are actually that. That's where they're calculating they're dealing with the initial fact that these are starting out at 0. So m hat and v hat. M and vt themselves, this is essentially updating each of these. So you'll notice that it's m based on the previous t. They're updating as they go through it. They are essentially creating more and more of a estimate of the first and second moments. And these are vectors. Obviously, they're across the weights. So that's essentially creating almost a learning rate for each. The first one is on the first power and then second power, so this is squared. We calculate these adjustment values just to deal with the fact that these started at a 0. And then we're going to update the weights. So weight t, this is very simple. So this part is exactly like what we had from trying to highlight the bottom row, but up to here is exactly what we had for classic. We're subtracting the gradient, but instead of subtracting the gradient, we're using this formula to update the parameters. Parameters are weights. Alpha is the learning rate. So usually learning rates, or step size as they call it, you're multiplying by the rest of this to scale this. And you're putting in the two hat values, which were based on these, just to adjust them so that they're not so biased initially towards 0. That is essentially ADAM. It's a little bit more complicated than your classic backpropagation, but not a whole lot. This is not terrible to implement in Java or another programming language. They discuss the algorithm. And they talk about that initial bias correction, why that is needed, and how you are calculating the two hat values that are very necessary for that. I will admit I have not read through this part and find it somewhat very complex. They're doing some analysis of the convergence. This is essentially proof for why it works. And then they quote related work. And then experiments where they sort of empirically prove through experiment why it works. And with the theorems, they attempt to talk about why it, sort of proof-wise, why it works. Related work, RMSProp and AdaGrad, those are two other very similar training techniques that existed prior to ADAM. And this is just straight sort of from the paper, but I like looking at the pseudocode a little bit better, but I reproduced it there if you're interested in it. This is a really good diagram. I did not create it. I have links to where this is where I found it. Yeah. So anyway, and then he cites it to the original author. So you can definitely want to give credit where credit is due. This is a very, very good diagram of this. It's an animated GIF. So this is essentially a search space. So you can think of this as a rugged sort of two-dimensional plane. Star is the lowest point. That's where you want to get to. And it's sort of like marbles rolling down a ridge. This is stochastic gradient descent, which is the slowest one. So that's your classic backpropagation. It's eventually getting there. The one that gets there really first is added delta, and it seems like green momentum starts out slow, but then really, as you can see, builds up the momentum and then blasts right past it. So just your different training methods. Atom is not on here because when this was created, atom did not exist, or at least was not all that common yet. But you can definitely see some of them, like momentum. It's very obvious that it starts to really build that momentum, the little green ball, and shoots right past it. SGD is just slowly, methodically working there, and it doesn't even make it. They give up and reset it because everybody else has made it. Keras and TensorFlow has a variety of these techniques available for you. The ones that are highlighted, they have stochastic gradient descent and atom. I believe there's other ways you can get to some of these. I'm sorry, these are all of the ones that TensorFlow has. I honestly have no idea what FTRL is, and I'm familiar with the other ones. The ones that I've highlighted are probably the ones you're the most interested in. I would be tempted to highlight RMS-prop as well. You can definitely experiment with these and get potentially better results. Where you specify it is down here with the optimizer. If you specify one of these that means a learning rate, you'll pass in a class here and actually pass in the parameters as well. You can go to the TensorFlow documentation and they show you, or Keras anyway, and they give you the actual class names for this. But you can just use any of them just by putting its name in here. You'll need to put an object in there if you want to specify even additional parameters. These are some of the results that I got trying these out. So you can see that on the miles per gallon data set, we got basically different results. And some, like you notice, momentum needed a lot more training than, say, atom, showing the last successful or the last number of iterations. So atom converges pretty quick. I'm pretty fond of that training technique, and I use it often. Adagrad is also pretty good as well. So Adagrad I like. RMS-prop definitely I've seen it has uses. I will try between these and look at them when I am training neural networks, and I often start with Atom, but then we'll try Adagrad or RMS-prop. There are probably better, more scientific ways to pick those, but that tends to work pretty well for me. All right, that is the end of this module. Thank you for watching this video on how to train a neural network. In the next video, we're going to literally calculate a neural network from scratch. We're going to see how to export the weights from Keras and use those to actually calculate what the output of the neural network would have been. This removes all magic from the process. This content changes often, so subscribe to the channel to stay up to date on this course and other topics in artificial intelligence.